especially when I'm going to remove the sound. That was pretty good. The only thing then is that the heights are different here, so bring this down to about the same place. Should be flashdach. Agus sin magnéad. Agus nar titan sé tríd. Was I got the came loose out titan sé. Well, no. No, ach tas going to loose gearú. Once again, look at the loose gearú or the hitting sé. Má sé sin says. So we're hitting name would go down. Agus gauntness air, the more air freaking in there. Titan sé le 8.1 meter second. Agus sin a hórdaí and so.
Now, when it comes to current, there are two types that you need to know about. Alternating current, which we often write as AC, and direct current, or DC. In an alternating current, the direction of the current is constantly swapping back and forth. So the charge flows in one direction, then the other direction, and back again. We get these alternating currents whenever we use an alternating potential difference, or alternating voltage. So one that fluctuates between positive and negative. We can see this if we measure the potential difference or current over time. They constantly fluctuate between negative and positive. And at the circuit level, this means that the direction in which the charge is flowing will constantly be swapping back and forth. Here in the UK, all main supply electricity, which is the electricity that comes from our plug sockets and powers our computers and kettles and so on, is AC. And specifically, UK main supply is 50 Hz and around 240 volts, which means that on our bottom graph, the potential difference fluctuates from positive 240 volts to negative 240 volts and back again 50 times every second. And so the current would also fluctuate at that same rate. One thing we should mention is that you'll sometimes hear that the voltage is 230 volts rather than 240. Basically, it can be either in the UK, so they're both correct as far as your exams are concerned. Direct current, on the other hand, is produced by a direct potential difference, which is either positive or negative the entire time. So the charge is always flowing in the same direction. We find direct current in things like cells and batteries, like those in your phone or a calculator. The last thing we need to cover is that in order to get these potential difference versus time graphs, we use devices called oscilloscopes, which display the graphs on a monitor. Anyway, that's everything for today. So hope you found the video helpful. If you did, then do share it with your friends, and we'll see you next time.
So for your GCSEs, you need to know what DC and AC look like on an oscilloscope. So this is my oscilloscope, and it's worthwhile just taking a look at what the oscilloscope actually does. Okay, so let's turn mine on. The first thing that you'll spot here is that there is a little dot that's traveling across the screen. It's traveling across really, really slowly. In fact, it goes through one of those little orange squares every second. 1, 2, 3, etc. Now, what a oscilloscope usually does is that it goes across a lot quicker. This dot goes across a lot quicker. In addition to that as well, the vertical axis is the voltage. Okay, so it's time and voltage, that's all it is. So let me just speed it up. Okay, so faster, 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 faster. So now it's tracing across really, really quickly until you have something that just looks like a straight line. Now what I have here is I have a battery, okay, so just a standard battery. I'm going to plug this into here. The battery is about 1.4 volts. It should be 1.5, but it's a bit of an old one, so 1.4 volts. Take a look at what's happened. The line has moved up by 1 square and 0.4 of a second square. In other words, it's moved up by 1.4 volts. Unplug it, goes back to 0. So add it in, 1.4. down to 0. 1.4 down to 0. What happens when the direction of the current is reversed? Pause the video here and sketch what you think the oscilloscope trace will look like. This time, instead of the battery just going straight into the oscilloscope, I've got it going into a special little device here where I can change the direction of the battery just slowly by turning it. Take a look at what's happening to the line. Okay, so if I was to put it in a positive direction, so that's the direction of the current, is a straight line that is up like that. If I then reverse the direction of the current, which I can do using my little device, then the line goes down. Let me just zoom in on that line for you. Okay, so this is what it looks like for a reverse direction of the current, and that's what it looks like in a positive direction of the current. And I can just turn my device and it'll change direction. Okay, so if you imagine that I'm going to plug that device in and turn it really, really, really quickly, what sort of a signal might you get? Have a think. An electric current in a circuit that repeatedly changes its direction is called alternating current. Sketch what you think an alternating current trace might look like on an oscilloscope. Remember, the x-axis is time and the y-axis is the voltage. Pause here and make your prediction. So, did you guess right? Essentially what we have here is we have something called a signal generator. The signal generator is giving an alternating current. In other words, it's got the current going in one direction, then the other direction, and then back again repeatedly. That is shown on the trace here by having forward direction, backwards direction, forwards direction, and a repeating pattern. And this is the kind of current that you get from a mains power supply. In other words, this is the current that you get out of the wall.
Hello, I'm Bruce Yaney, and today I'd like to look at visual proof of the difference between a direct current and an alternating current. So let's take a look. I have a battery pack, I have a light bulb, and batteries are said to be direct current. So when I attach the battery pack to the bulb, electrons are flowing out the negative side through the bulb and back to the battery pack. This is a direct current. The electrons are always flowing in the same direction. This bulb is constantly on because it's a steady stream of electrons, always flowing through the same way. So let's wave this in the dark and see what it looks like. If you wave this type of light in the darkness, you'll see a steady stream of light with no breaks in it because it's a continuous source of electrons going through the bulb. So this is a direct current because the electrons are always flowing in the same direction. Now, the household electricity coming into your home is an alternating current, and it's cycling 60 times per second. So when I plug this in, and in this case I've lit a little neon light, and when we look at this bulb in the dark, it also appears to be a steady stream of light. But the electrons are actually switching directions every 60th of a second. So the electrons are constantly going back and forth. So this bulb is not always on because the electrons are actually going in one direction, stopping, and then going back in the other direction. Now, let's try waving the neon light in the dark and see what its path looks like. When we view this light in the dark, we'll actually see breaks in the stream of light because the electrons have stopped flowing in one direction and are starting to reverse to flow in the opposite direction. So when I move this light around fast enough, it's allowing us to see that change that's occurring every 60th of a second. This next piece is going to use two lights that are hooked up to diodes. Now a diode allows electricity to flow in one direction, but not in the other direction. Kind of like a one-way gate. It allows electrons in, but it doesn't allow them out. The orange bulb has electrons flowing in one direction, but it's not able to flow in the opposite direction through it. And the green is able to flow in the opposite direction, but not in the first direction. So when the orange is on, the green is going to be off. So let's wave this in the dark and see what this looks like. With this piece, we're seeing alternating colors. The orange is on when the electrons are flowing in one direction, and the green is on when the electrons are flowing in the opposite direction. Alright, so there's our visual proof of direct current versus an alternating current. I hope you enjoyed this segment and come back again because I have other things I'd like to show you. Okay, thank you. Bye.
A sine wave is a smooth, repetitive waveform. One completion of the repeating wave pattern is called a cycle. The time it takes to complete one cycle of the wave is called the period. In this example, the time it takes to complete one cycle is 0.25 seconds. So this waveform has a period of 0.25 seconds. The unit of measurement of wave frequency is called hertz. A hertz is equal to the number of wave cycles occurring in 1 second. For this wave, there are 4 cycles in 1 second. Given that frequency is 1/t, or period, then the frequency is 4 cycles in 1 second, or 4 hertz. The highest point or the lowest point of an AC waveform are referred to as peaks. Peak amplitudes or values can be measured in the positive direction starting from the baseline or in the negative direction. The peak-to-peak value is measured from the negative aspect of the waveform to the positive aspect. In symmetrical waveforms, the peak-to-peak value is twice the peak value. AC meters generally do not read in peak values or peak-to-peak values, whether it is voltage or current. AC meters will read in root mean square or RMS values, also referred to as effective values. If the DC is set at 10 volts, this will produce a certain amount of power and heat in the resistor. If you regulate the AC input in the AC circuit until you reach the same amount of power and heat, it will require 14.14 volts peak to be as effective as the 10 volts required in the DC circuit. This is due to the alternating characteristic of an AC wave whereby voltage oscillates between peak-to-peak maximum values. Thus, on average, full voltage is not being continuously delivered to the AC circuit to generate the same power as a DC circuit. Therefore, To compensate, AC circuits need higher voltage input. When the power in the DC matches the power you produce in the AC voltage of 14.14 volts at its peak is as effective in producing the same power as 10 volts in a DC circuit. Therefore, we can define the AC peak value as 1.414 times 10 volts or 10 RMS, which equals 14.14 volts. You may also want to determine the RMS by dividing the AC peak value of 14.14 volts by 1.414 to get 10 volts or 10 RMS. Therefore, an AC voltmeter connected across the resistor in the AC circuit would read 10 volts.
È ancora buio pesto. Meglio usare la dinamo.